Good afternoon, everyone. I'm Yuchen Liu from Northwestern University. It is a great pleasure for me to introduce my former advisor, Professor János Kollár, at Princeton University, our AMS Invited Address speaker today. Professor Kollár began his mathematical training in Budapest, earning his bachelor degree in 1980 from Eötvös Loránd University, and he completed his PhD in 1984 at Brandeis University under the supervision of Teruhisa Matsusaka. Professor Kollár is one of the central figures in modern algebraic geometry, where questions of birational classifications, moduli, and singularities come together in powerful ways. Over the decades, his work has profoundly shaped the field, particularly through ideas connected to the minimal model program, the geometry of rational curves, and foundational contributions to our understanding of singularities and moduli spaces. Many of us also know him through his influential books and expository writing, which have guided generation of researchers and students. His contributions have been recognized with major honors, including the AMS Cole Prize in Algebra, the Nemers Prize in Mathematics, and the Schall Prize in Mathematical Sciences. He was also a plenary speaker at the ICM in 2014 in Seoul. Today, Professor Kollár will speak on which surfaces can be built from circles, and please join me in welcoming Professor János Kollár.
Thank you. Thank you very much for coming. So I thought that instead of trying to explain my technical contributions to modern algebraic geometry, I try to say something about some very classical and more elementary topics, and then I hope at the end I still have time, sort of how these very elementary questions led to some contemporary questions in algebraic geometry. So there will be some pictures. They are not mine, especially as nicer they are, the more likely that they aren't mine. And so I especially recommend everyone to look at the homepage of Herwig Hauser, has lots of nice pictures, and also Niels Labes have actually lots of nice pictures and also animations. Okay, and so my main topic is which surfaces can be made out of circles, but clearly one should start with the more elementary questions, which surfaces can be made out of lines. And this has been known for some time, that there are only two surfaces that have grids of lines. So now the planes, of course, they have been known for a long time. Now, as far as I know, the first time this was outlined that the one-sheeted hyperboloids also carry two families of lines. It's by an article where it says Christopher Wren. He is actually Sir Christopher Wren, the architect of St. Paul's Cathedral. And at Volume 4 of the Philosophical Transactions of the Royal Society. So the article itself is in fact in Latin, but in the table of contents, it is in English. Yeah? So it's sort of strange that it's done that way. And then there's also an illustration of this, one of the early mathematical illustrations. Actually, there are it has a mathematical part, so it was put together that there's a hyperboloid, and now the other illustration is also, well, we think of it as mathematical now. Actually, it is described in the article as the double matrix. And so, well, I learned from here the original English meaning of matrix, okay? Which I didn't know before. So, okay. Yes, and there is also an architectural illustration of the one-sheeted hyperboloid. So it's actually fairly popular. You can find this over many places. Now, then the next question is which surfaces carry grids of circles, and this turns out to be a much more complicated question. So the first person who looked at this very seriously was Dupin in 1803, and then there were some contributions by Kummer, Darboux, and Bertini. So Darboux especially wrote some very significant articles, but it is only in the last 45 years that the list was completed, and it was actually proved that the list was complete. So in some sense, this very classical question has the complete answer was actually done only fairly recently. Now, the first observations that in fact we don't assume that we are doing algebraic geometry, but we are. So if you have a smooth surface in R3 or in Rn that contains at least two circles passing through every point, then the surface is in fact algebraic. So in R3 then is given by just one polynomial equation. And so now there's nothing special about circles here in general. If there's a surface that contains two algebraic curves through every point, then it's an algebraic surface. Okay. And so now from now on, I will look mostly at algebraic surfaces in R3, and we will go by degree of the polynomial equation. So degree 1 equation, there's the planes, there are lots of circles there. And well, the degree 2 equations, that's already a little bit interesting, but so first I want to settle what happens with spheres. They have lots of circles, not just there are two circles at every point, but through every 2 points you can find a circle. And so now it turns out to be that there are very few surfaces where that contain a circle through every 2 points. And so there's of course the plane. Then there is a sphere in R3. So even if we are in Rn, it is just the sphere in R3. And there's one more, the Veronese surface, that sits inside S4. So what is this? It is sort of given by so the simplest representation is that if you map to projective 5 space, then you just write down all the degree to monomials, and you map projective plane there. Now, if you take the first 3 coordinates here and just add them up, then you get a surface in P3 or in R3. Well, this is known as Steiner's Roman surface, which was, I believe, the first concrete representation of the projective plane inside R3. And now it is not easy to squeeze the Veronese into the 4 sphere. I actually not sure if it can be done by just rational equations, but at least if you throw in some square roots, then here's a representation at the bottom that ends up actually in the 4 sphere. So maybe sort of what's interesting about this that it's in fact an isometric embedding. That is not just algebraic isomorphism, but from the differential geometry point of view, that's an isometric embedding as a minimal surface. Yeah. Okay, so then these are the surfaces that contain lots of circles. So through any 2 points there is a circle. For the others, there are many fewer circles. In fact, it's very easy to see that otherwise there are only finitely many circles through any point. And we will see, or at least I will say that in fact the maximum number for this turns out to be 6. Okay. Now let's go back to degree 2. Okay. And so now here there are 2 families of circles unless there is rotational symmetry. So maybe the simplest example that you might know it is a circular cylinder. And so, for instance, you buy a nice salami, and if you are cutting it sideways, then you get ellipses. But if you cut it exactly transversally, then you get circles. Now, what happens if you buy an elliptical salami? Now, it's probably not easy to get in stores, but if you buy an ordinary round salami and you sit on it, then you get an elliptical salami. And then you can see that there are 2 ways to slice it that you get circles. So most slices are still ellipses, but there are 2 ways to get circles, sort of slanting one way or sort of slanting the other way. And so that means what happens here, that if you destroy the rotational symmetry, then you seem to get actually more circles, which is sort of surprising. You would think that rotational symmetry is the one that creates circles, but in fact it seems that it collapses these 2 distant families of circles into one. So now here's an ellipsoid example that, well, okay, it's pretty hard to see that this is not rotationally symmetric, but believe me, it is not. Okay. Now the next, then it's up to cubic big surfaces. So it's a degree 3 equation. Now here there are very few lines, well, not very few, finitely many lines. It turns out that over the complex numbers, there's always 27 lines. That was proved by Cayley and Salmon. And the Schläfli showed that the number of real lines can be 3, 7, 15, or 27. So these are the only possible values for the real lines. And then here's a computer-generated image. Now, actually, it's interesting that after Schläfli proved that the maximum so the 27 is possible, for a long time there was no actual example. And so it was Wiener in 1869 to actually construct the cubic surface that contains 27 lines that are all real. Okay, now, well, what about circles? So more generally, what about conics? So, well, let's take one of these lines and then a plane that passes through these lines. Now the surface has degree 3, so when you intersect it with the plane, you get a plane curve of degree 3. But it contains a line, so that means that it has to be a line plus a degree 2 curve that is a conic. So in particular, this means that if you have one of these cubic surfaces that contain 27 real lines, then to every point that's not on a line, there are 27 conics. Now, I haven't seen an actual picture of it, and probably someone made one. It would be impossible to see what's going on, but sort of that's the fact. And then then these conics are real if and only if the lines are real. Now, well, okay, these are conics. How many of these can be circles? Now, it turns out that there can be at most 6 of these that can be families of circles. I will hint at the explanation later. So here's an example. Let's consider this explicit example of the cubic surface. Now, and then, well, you either check or believe me that there are the 6 real lines there. And the claim is that all 6 of these, they give actual families of circles. Let's just see one example. So the line, which is the last line, the t minus 1t. And so then we write down the general a plane that passes through the z equals a constant times x plus y. Yeah. Now, and then to understand the intersection, I do this trick that I do the substitution for z only at the red z's. So you see there is a red z at the beginning, red z at the end, but inside there's an x squared plus y squared plus z squared. That I leave untouched. But if I do this substitution, I can cancel the x plus y. So then I see that I have the intersection of, after I cancel the x plus y, then I just get the sphere there. So it's a sphere intersected with a plane. And of course, if I have a sphere intersected with a plane, that is a circle, okay? So you can play exactly the same trick for all 6 of these, but I sort of leave this up to you. Now, we will see later more or less why at most 6 of these can be circles, okay? And so here is an example of these families. There is the orange line and the black line. They are sort of thicker, and then the corresponding families of the two circles. Okay, now let's move up in degree 4. So what's maybe the next simplest surface that we know? That just ordinary torus, okay, round torus, completely round. Now, this slide is for algebraic geometers only, but it's a challenge. So what is a torus as an algebraic surface? So as algebraic geometers, you probably learned about the classification of algebraic surfaces. And, well, it sort of illustrates the nature of modern algebraic geometry, that so far I have not encountered any algebraic geometer who could tell me what the torus was in terms of the classification of algebraic surfaces, okay? So, well, so I think in this audience, I hope someone comes to me at the end. Now, if you already sort of heard my talk and I told you, then it's not fair. But if this is the first time to hear this question, and you can tell me by the end of the talk, okay, I think I will send you some presents, okay? Okay, so what this has to do with circles? Well, there are sort of the standard circles on the torus that we know. I mean, it's obtained as just sort of by rotating a circle. So there's the blue circle that's rotated around, and because of the rotation, we have the red circles. Now, it turns out that there are 2 more families of circles on the algebraic torus, on the round torus, and these were discovered by Villarceau in 1848. And so they sort of start on the outside, but then they go through the inner hole, okay? So if you do this very carefully, you get these 2 more families of circles. So, but it was first written down mathematically by Villarceau, but there are in fact some carvings in the Strasbourg Cathedral from the 1500s, which sort of seem to suggest that the carver also knew that there are these circles going around the torus. Okay, and so now this leads us to the topic of cyclids. So these are the degree 4 surfaces that contain lots of circles. Now, when I first read about cyclids, I didn't know what they were. So then I went to the Oxford English Dictionary, which told me that is the envelope of a sphere whose center moves on a fixed quadric and which cuts a fixed sphere orthogonally. Now, I still don't know what this means, but I am absolutely amazed that in 1896 this was a definition that an educated Englishman would just say, oh yes, now I know what a cyclid is. Okay, and another interesting thing that, so there is Felix Klein Encyclopedia of Mathematics, and it devotes actually 60 pages to these cyclids. So it seemed that 100 to 150 years ago, this was a much better known topic than it is now. And so now, in fact, it's sort of not too hard to define it in a way that's understandable to ourselves, so that if you think of R3, compactify it to projective 3 space, then at infinity there is the ideal conic, so it has no real point, but it's there, it has lots of nice complex points, and this is a degree 4 surface that vanishes twice along this ideal conic. And so then its equation is, well, start with the equation of the ideal conic. You have to square it to vanish at infinity. Then if you take it just 1, then you have to take the equation at infinity. So that's why this L1 has to be linear, so that there is a room for that other homogeneous coordinate. And there's arbitrary degree 2, which vanishes twice at infinity. And now Darboux proved in 1880 that the cyclids can have 10 families of conics, and up to 6 of these can be families of circles. So this 6 again comes up here. And then sort of here is an illustration of the cyclid. You should think of a cyclid as just a perturbation of the torus. So you are destroying well, so you should think that the torus has 2 rotational symmetries. So one of these is actually visible in R3, the other not, but it's clearly, there seem to be some symmetrical ones. And so now the Villard-Saut circles, they are not involved with the rotational symmetries, and so that they just stay, these 2 families, they are in red. But the other 2 families, they actually break up into the same thing when the round salami becomes elliptical salami, becomes 2 families of circles. The same thing happens here, that on the torus, the small circles now become these 2 orange families, and the large circles become these 2 yellow families. So again, I want to emphasize that through every point of this surface, there are these 6 circles, not just that one point here. So every point there are 6 circles. Okay, so well, what's the plan of the proof? How can we more or less try to understand what's going on? So the first thing we have to notice that conics are easy and circles are hard. So if you are doing algebraic geometry, then understanding what is a conic, that's easy. Understanding what is a circle, that's hard. So if you just work in the plane, you write down any random degree 2 equation, that's a conic. But to make sure that it's a circle, then one of the coefficients has to vanish, and the x square and y square coefficient, they have to be the same. So it's not just that you write down random numbers, but you have to make sure that something special happens. Now in the space, it's even more complicated. If you have a space curve and its random projections are conic, then in fact it's conic in some plane. Whereas if you start with a circle, then projections are just ellipses. So that means it's not easy to see when you are getting a circle in 3 space. Yeah? And now then if you parameterize it, so that if you start some degree 2 polynomials in some variable t, and you send t to these homogeneous equations, then if these QIs, they all have degree 2, then you get a conic. But you are getting a circle only if Q0 divides the sum of the squares of the others. So it can be a rather subtle condition, and so that means that's why it happens a lot that I can very easily tell that, for instance, on the cubic there are 27 conics through a point, but it's pretty hard to say when they are exactly circles. Okay. Now, but again, a nice old theorem comes to help us, is due to Hipparchus, and then it was also used by Ptolemy. The first proof I'm aware it is by Halley of Halley's comet fame, and so it's again, the title of the article is actually quite long. It seems that these people like sort of long titles. Now, this article is actually in English, and it has a very modern feel. So, you know, it's stated as lemma 2, and then there's a clear explanation, and then, okay, there's a clear illustration. So this really reads like it could be from a completely contemporary geometry book, except for the last part of the statement of the lemma, which says, but this not being vulgarly known must not be assumed without a demonstration. Okay. So, well, it seems that now these are vulgarly known, so I think we don't need to have some special demonstration for that, but anyhow, if you are asking some, there is one here. Okay. Now, what is the consequence of sorry, did I actually state Hipparchus? Yeah, yes, okay. And so then, okay, so I have the stereographic projection. So what happens if I have a circle that's contained in a surface that's Rn? Now, if I look at the inverse of stereographic projection, then Hipparchus says, well, I get a circle, but I get a surface inside the n-sphere, but Hipparchus says that the circle maps to a circle. But you see, a circle in the n-sphere is the same as the intersection of the n-sphere with a plane, which is the same as a conic. So if I have a conic in the n-sphere, then it's automatically a circle. So that means that if I manage to write down my algebraic surface, not in Rn, but sitting inside the n-sphere, and I can count conics there, then these conics are automatically circles. And so then if I go back to the plane by stereographic projection, then these circles on the sphere, they become circles in Rn. Okay? So that means it's a little bit sort of more complicated, but now I'm in very solid algebraic geometry ground. I just need to count conics for a surface that happens to be inside Sn. And now, then sort of maybe here is the explanation why the cyclids were such an important topic, because the surfaces that I will use, they are the intersection of the sphere with another quadric. So from our modern point of view, that's the intersection of two quadrics. So these are the degree 4 del Pezzo surfaces. So that means that these people studied cyclids. In fact, they were studying the degree 4 del Pezzo surfaces, okay, which is a fairly interesting topic now. And now, if you take one of these intersections and you project it from a point that's not on it, then you get a cyclid, a degree 4 surface. But if you project from a point that's on it, that lowers the degree, so that means you get a cubic, okay? But now you see why we get the same number 6 for degree 4 surfaces and for cubics, because they are just the two kinds of projections of the same problem that exists inside S3. Okay, so that's nice. Okay, now, well, so then there are actually lots of higher degree examples, and they are not easy to classify. It is fairly easy to see that such surfaces can exist only up to degree 8, okay? And they are not easy to classify, but turns out that there are at most 2 families of circles on all of them. So in fact, sort of the most interesting examples that we have up to 6 families of circles, they are in degrees 3 and 4. Okay, so these in fact all come as projections of other Del Pezzo surfaces, and we know that they can go up only up to degree 8, and there's a Veronese surface in degree 9, so there's the explanation why they go up only up to degree 8, but it turns out it's sort of not easy to understand which projections will sit inside the sphere. So if I just project it random, then it will not sit inside the sphere, and it's sort of not that easy to understand exactly what happens here. Now, okay, so maybe this was the question: what happens with this very classical question? How can you move to some more modern, in fact, some very contemporary algebraic geometry? Well, for simplicity, I will mostly just look at some hypersurfaces. That means that algebraic varieties that are defined by just one equation. So I just take one polynomial f, and then I'm looking at the 0 set. And again, the main invariant is the degree of this polynomial, that's d. Okay, and so now I would like to go back to lines. So maybe, if you think of the examples of the hyperbola, 2 families of lines, so I can move along lines. So you can ask, if you have a surface of degree d, when can you move between any 2 points on a path that's either piecewise linear or piecewise conical, or something that we can reasonably understand. So if you have a one-sheeted hyperboloid, then in fact you can move between any 2 points on line. Start with so if you have 2 points and you take a line in one family through one other family, the other, they intersect somewhere. So there is no straight line, but if you just want to move on a path that's so broken at one point, then you can do that. Now, we know that a cubic surface contains only 27 lines, so for most points I can't even start if I want to be on a line. So what happens in higher dimensions? And so then again I have this hypersurface X inside Pn. Now it turns out that there is a linear path between any 2 points, if and only if the degree is at most n minus 1. So you see that quadric sits inside 3 space, so its degree is less than or equal to, and then you can go up in the dimension. Now, of course, there is you might say that already quadric is already on the one-sheeted hyperboloid where you could actually move lines. So the problem with this theorem is that in general, this is with complex lines, yeah? So that you can move along complex lines, but not necessarily real lines. And well, it's sort of not too hard to understand what happens with real lines. There are sometimes very few real lines, but there is always a real piecewise conical path. So that means the pieces of that path are not lines, but just conics. Okay, now of course, again, if you look at such a real hypersurface that can have several components, and of course you can't jump from one component to another on an actual real path, but as long as the points are on the same connected components, you can move between them using a conical path. Okay, so this goes to degree n minus 1. Let's see what happens. Okay, so now then, these are just lines and conics. And now if I think of lines and conics as just images, so if I just take arbitrary q0, qn, if they have degree 1, so linear in T, then the image is a line. If they have degree 2, then the image is a conic. So then there are these rational curves of higher degree that we might employ here, okay? And now then it turns out that if you have a degree n hypersurface, so you see for lines with complex lines you could go up to degree n minus 1. If you go to degree n, then it turns out there's always a piecewise conic path if you allow complex paths. If you insist on real paths, then it turns out there's a degree 4 rational curve path, okay? So, okay, so that sounds nice. You would think that there's a pattern here. I just need to use some higher and higher degree rational curves, and then I can move, but unfortunately, that's the end. If you take a general hypersurface of degree larger than n inside Pn, then there is no rational curve at all through most points. No matter what the degree, there is simply no rational curve. And so you might say, well, that's the end. There is nothing else we can do. So, okay, we could say that sort of one story ends here, but as sort of in good mathematics, well, once you completed a story, you should always ask, well, can I change something? Is there some way to continue? And in fact, there are several new stories that we can continue. Well, one is, so far we looked only at just hypersurfaces where there are these, starting with piecewise linear paths or piecewise conical paths, but now maybe you can understand what happens when there are through piecewise rational curve paths. And now it turns out that it's that is a theorem that if there is a piecewise rational curve path through any 2 points, then in fact there's a rational curve path. So you don't have to be piecewise. There's just one rational curve that sort of does the job. Now this is over the complex numbers. This is I think it's okay over the reals if you are in the same component, okay? And now so actually I spent a lot of my mathematical life on these rationally connected varieties because this turns out to be a very important class among algebraic varieties. It's very closely related to lots of topics, for instance, the positivity of Ricci, curvature. Then there's symplectic geometry. In fact, that's one of my favorite unsolved question I asked, that if you have one of these variety and you are forgetting the complex structures, you preserve only the symplectic structure, then so can you still tell that it's a rationally connected variety? Okay, so that's a interesting question, but maybe the main way they come up is through number theory. So these are the algebraic varieties where if you are defined over some number field, then you expect lots of points in that number field, or maybe it's finite extension. So that's I think sort of one of the main investigations that's still very, very active is to understand to what extent this statement is true, that these are precisely the varieties that have lots of points. I mean, the conjectures of mine in, I think by now, I don't know, by now 40 years old at least, they are a very, very active area which sort of tries to say this in exactly some very precise way. Okay. Now, then the other story is so rational variety. So far, I concentrated only on just rational curves, but it's similarly interesting thing to understand that you have not just rational curve, but rational surfaces, and so on. So how much can they be really completely freely parameterized? So you should think of a rational curve as you can just parameterize nicely with the line. So if you have a nice one-to-one or almost not one-to-one parametrization, not with the line with Rn, then you get the notion of a rational variety. And again, this has been very much investigated, especially for hypersurfaces. But of course, the degree is 1, that's just a hyperplane. Of course, by definition, that's just Rn. And then is Hipparchus' argument that says that degree 2, they are also rational. The stereographic projection shows that. Then it was Claps who showed that these degree 3 surfaces in CP3, they are rational. But the degrees 3/3 inside CP4, they are not. That was a major proof by Clemens and Griffiths, and the same holds in degree 4. Now in higher dimensions, and so, as soon as the degree is actually larger than n, then there aren't even rational curves. So clearly there cannot be a more variable rational parametrization. So this question is interesting. What happens below? And so I went down to 2/3 of n, but here the really big breakthrough was by Schraeder, who went to log n plus 2. Now, of course, here the really annoying thing is that maybe the answer should be 4. So there is not a single example of a smooth hypersurface of degree at least 4 that is known to be rational. So it is possible that the correct answer is just 4. Now that leaves us with degree 3 inside CP5, which turned out to be an amazingly complicated question. So maybe the first major article about this was by Morin in 1940, who presented a proof that they are always rational. Now this proof was wrong, okay, but not completely wrong. He showed that there are lots of them that are rational. Just when he claimed that this construction covers everything, it turns out to be no. The modern investigations, really the most important and understanding it came from Brandon Hessett. Okay, I mean, I just, and so, okay, of course, conjecturing that sometimes yes, sometimes no is not particularly precise, but he had a very, very precise proposed answer. When is the answer yes, and when is the answer no? And then, so there have been known that there were some constructions when it was yes, and it's only, well, and so the last, this preprint, it has been announced I think something like 5 years ago in some series of lectures by Kansavich that the answer is mostly no, but it's only now a few months ago that the preprint is actually on the archive, that for most of them the answer is no. So I hope at the Chicago meeting someone will explain this proof as part of this interesting development of modern mathematics. Yeah. Okay, now then another question is, okay, so we said a cubic surface, okay, it contains only 27 lines, so it doesn't have lines through every point, and I said that if the degree is larger than n, then it does not have rational curves through every point, but then, well, maybe this means you can actually count them, and then sort of here again, maybe this is by far the largest story that came out of it, the story of Gromov-Witten invariance. Well, okay, so and this is probably the simplest example, that if you have a degree 5 hypersurface inside CP4, so then, but it has been known for quite some time that it contains exactly 2,875 lines, and then Ellingshausen and Stromme computed well, I suppose that the conics might have been computed by Katz, maybe even the cubics, and sort of now we have some numbers which say that the number of rational curves of degree d is sort of this number. This is a Gromov-Witten invariant. But I believe that, and so these numbers exist and they are very solidly determined, but I believe we don't know what they count. And so the problem is that, well, one thing that can happen, that these various things, they should be counted with multiplicities, yeah? And now, well, with lines and conics and cubics, you know that on the general one, this multiplicity is always 1, okay? And so now in higher degrees, it's sort of not as clear what we are counting. And the other thing is that we know that there is no line through a general point, but for instance, it is possible that there's always a one-dimensional family of, say, degree 16 rational curves, okay? And so the answer can be infinite, but so this number doesn't show it. So I think it's known only up to degree 11 that it was proved that there are only finitely many on the general case. And now I think it says that I should stop in 1 minute, 1 second, so this 11 is a very nice place to stop, so thank you.
Thank you, János, for a great talk. Any questions for the speaker? Please.
I think it says go to your microphone because then everyone can hear your question.
Yeah, there are microphones at the aisle. Please go to that.
Okay, thank you very much. That was a beautiful talk, and I am interested about the conjecture of Hazard in 1999 about this cubic foifoil X3. Is it his conjecture does give a precise answer, or how would it should, if it would be true, what it should be?
Okay, Hazard is sitting right next to you.
yeah, perfect.
Maybe go to the microphone, Brandon, and answer the question.
Please.
So many people contributed to this, including Joe Harris and Kuznetsov and other people. but generally there's a relationship to surface geometry. If there's a K3 surface that you can see hidden in the cohomology, that's the condition to be rational.
Yeah, okay, but the answer would be then complete.
If this is true, yes. And even the new breakthroughs by Kontsevich, Katsarkov, Pantev, and Yu, I don't think that they actually give a precise answer. They only say that some of them are not rational. And that was a long-standing problem for many years.
Thank you very much.
More questions?
Well, then I will take the privilege of it. Do you know anything about conics on quintic threefolds? Or even degree rational curves?
Conics on quintic threefold. I mean,
over the real numbers.
oh
Sorry.
yes, over the reals. No. So, but wait. So, no. So these results when I went from lines over the complex to conics, I always obtain them that if there is a conjugate pair of lines that they meet at a point, it has to be a real point, okay? So, just think of x squared plus y squared equals 0. In the real it's a point, but you should think of it as a conjugate pair of line. But a small perturbation of it, if you do it in the right direction, is x squared plus y squared equals epsilon. If epsilon positive, then you see this little ellipse, yeah? Now, I think that if you have a quintic threefold, it has finitely many lines. They are usually disjoint. So that means that this trick will not work. I don't know about real conics. Yeah, thank you.
More questions? So if not, let's thank János again.
Thank you.